In this video, we're going to talk about how equilibrium relates to acids and bases and the pH scale. So just a quick review. When we're talking about equilibrium systems, we have systems where both forward and reverse processes are happening at the same rate, resulting in no net change. But at that equilibrium point, we're going to have a certain ratio of product to reactant, and we describe that with a value of K. So for a generic reaction of A plus a solid B, not a bad grade, it gives you 2C and then D. We would write this K expression with the products C and D using their coefficients as exponents in the expression. And also we leave out pure solids and liquids, so our only reactant would be A. Just a review of what an equilibrium expression looks like. So with respect to acids and bases, there's a couple different scenarios. K always means the same thing. It's a ratio of products to reactants for any process. Now some bases are metal hydroxides. Most of our strong bases are metal hydroxides, but not all metal hydroxides are strong bases. Your alkali metals and your larger alkaline earth metals are, but things like iron hydroxide, magnesium hydroxide, not so much. So when we're looking to figure out the pH, we can use two possible ions to really get there. When we're talking about bases, we're going to be talking about hydroxide ions. When we're talking about acids, we're going to be talking about hydronium ions. So a weak base, magnesium hydroxide, is a slightly weak base, and it's just a slightly soluble hydroxide. So the process of that contributing hydroxide ions to solution, you have a solid that breaks up into its magnesium, the metal cation, and your anion, which in this case is hydroxide. You get two hydroxides for every magnesium. So in this case, I'll tell you that the KSP for magnesium hydroxide is 5.61 times 10 to the negative 12. Not a large number, so it's not a very strong base. But we could figure out how much hydroxide would be present in solution and calculate the pH from that. So given that we get two hydroxides for every magnesium hydroxide that dissociates, and given our KSP, we can just write the K expression as our magnesium concentration times our hydroxide ion concentration squared. Now, with equilibrium systems, we're going to create a Rice chart, or most people call it an ice table, but you got a reaction here. So we're always going to assume that initially, with this type of situation, that our initial concentration of product is 0. But we know that it's going to go up by some amount, and that amount is going to be relative to the stoichiometric ratio in the chemical equation. So given those values, we're going to say this magnesium goes up by some amount, hydroxide goes up by twice that amount. But then when we write our equilibrium expression, we still have to square that hydroxide because of that coefficient of 2. So our KSP expression looks like 5.61 times 10 to the negative 12 is equal to X, which represents our magnesium ion, and 2X, which represents our hydroxide. We end up with 4X cubed equals our KSP. When we solve for X, we get that value. Going back to our Rice table, at equilibrium, we're going to have 2X hydroxide ion. So that means that's our hydroxide ion concentration. And when we take the negative log of that value, we get our pOH, which we find to be 3.61. Given that the pH is going to be 14 minus our pOH, the pH of this system would be 10.39. So we can use KSP for weak metal hydroxides to get to our pH. For weak acids, we use something called Ka. So Ka, for acids, when you put them in water, they donate a hydrogen ion, and they're going to produce a hydronium ion in the conjugate base. So there's two scenarios we can have. We can have, given the Ka, find the pH. Or we could go the other direction where we're given the pH, find the Ka. So for this, we're just going to go, given the Ka, find the pH of a 0.1 molar solution. So again, we assume that none of it's ionized at first and that all of our molecules are in the weak acid form. But that's going to go down by some amount, and that amount it goes down by is going to be equal to the amount of hydronium ion you form, as well as the conjugate base. We don't worry about water because it's a pure liquid. So now we just have to set up our equilibrium, our K expression, to be our hydronium ion and our conjugate base times our, there should be a bracket here, over our weak acid concentration gives you your Ka. So we're going to use X to represent our concentrations of hydronium ion that form and our conjugate base that form. And we're going to plug those into our K expression, dividing by 0.1 minus X. If the Ka, or Kb in another problem, is smaller than 10 to the negative fourth, you can neglect the loss. And we'll see in the next equation as to why. But so you can just ignore this loss because it's going to be negligible compared to that initial concentration. And we'll see that. So when we solve for x, you get a value of 1.0 times 10 to the negative fifth. If you were to subtract 0.00001 from that value, it doesn't put a dent in it, so you can just ignore it. And when you take the negative log of that value, you get that the pH is going to be equal to 5. Again, x represents our H3O plus concentration. Negative log of that gives us the pH, which is a value of 5. When we're looking at weak bases, we use something called Kb. So this is for non-metal hydroxide weak bases. So a base, when you put it in water, accepts a hydrogen. It does the opposite of what an acid does, and it's going to produce a conjugate acid and then a hydroxide ion. Again, we can use the hydroxide ion to get back to our pH of the solution. So this one, we're going the other way, where you're given a pH, and it's asking you to determine the Kb. You still have to set up a rice table for this, a rice chart. So initially, it gives us our initial concentration of the base is 0.2. We don't worry about water. Again, it's pure liquid. And none of it's in its ionized form. But instead of solving for how much ionizes, we're given the pH. So if the pH is 10, we can use that to get to a pOH of 10 to the negative 4. And our hydroxide ion is going to be equal to 10 to the negative pOH, so it will be 10 to the negative 4. So that's going to be our hydroxide ion concentration at equilibrium, hydroxide ion, as well as our conjugate acids concentration. Then we can just plug this all into our K expression to get a Kb, which would give us 5.0 times 10 to the negative 8th. And again, if the K is really small, like 10 to the negative 8th, when you subtract that value that you get, it's not going to make a dent in the concentration at equilibrium. So we can ignore it. Anyway, that's how equilibrium relates to acids and bases.